the second speaker, we have Ali Sadegh. Okay, he is a researcher at the Institute of Interdisciplinary Research in Fundamental Science in Iran. His research interest is in the sets, theories, and mathematical logic. So over the years, he has collaborated with accomplished set theorists, and Joel David Hampkins was one of them he met during his undergraduate studies. He will talk with us about his views on mathematics from a multiverse perspective. So after you, Ali, all yours.
Hello, everyone, for your introduction. And I would like to say hello to every friend here, especially you and Chu Yao and some other friends I see here. Yang, hello, everyone.
Hi.
And thanks for your invitation. So let me share my screen with you so that I can start my talk. Oh, by the way, congratulations on the establishment of the Association of Malaysia. I wish you all in the future years.
Thank you.
So please tell me you can see me and hear me perfectly and see my slides in
yes,
good quality. Okay, so let me see whether I can minimize this thing. Well, okay, let me start. My talk is about the multiverse view in Foundation of Mathematics, and it's a new approach in the philosophy of Foundation of Mathematics, which is derived from advancement in forcing and set theoretic technical theorem, which I guess some of you might be familiar with. Most of the results presentation are due to Joel Hampkins and his colleagues, and I would like to try to give a brief exposition of the area without getting into too much technicalities, which might be boring for your audience. So let me start. Well, a little bit of history first. What's the origin of the problem? What's we are to achieve here? Well, we all know that inspired by Cantor's proof of the uncountability of the continuum, Hilbert a very simple fundamental question on top of his famous list of 23 important mathematical problems of 20th century. Well, what was Hilbert's first problem? He simply asked how many real numbers are there. So this is Hilbert's first problem. It's originated from Cantor's hypothesis, in which Cantor speculated that the number of reals is the minimum possible, namely because we know that they are uncountable. We know that there are more real numbers than the natural numbers, but we don't know actually how many, which aleph, which uncountable aleph. Maybe aleph 1, maybe aleph 2, maybe aleph or even higher. Nobody. So that was Hilbert's question. How many real numbers are there? Well, came Zermelo and Frankel. They provided an axiomatic for the set theory and the language of set theory via ZFC. And they provided actually the genetic code of the mathematics and told us that every mathematical object could be expressed in the language of set theory with just one binary predicate named the membership and a few relatively simple and so-called intuitive axioms of set theory. And basically they taught us that every mathematical object is the same as any other mathematical object in the sense that they are all sets with particular properties. Well, Gödel proved that assuming the consistency of Z is incomplete. Uh, so also Gödel, so the statement of the Gödel says that, well, there are statements in state theory that could not either be proved or disproved ZFC, assuming that ZFC is consistent. So one such example, Gödel proved that ZFC cannot prove the negation of the continuum hypothesis. So it could not be proved that the hypothesis is false, that ZFC is consistent. So came and proved the other way around. He proved that ZFC cannot prove the truth of the continuum hypothesis. So we derive from these two statements that the existing mathematical tools provided by the axioms of ZFC, which is basically all the mathematical tools, normal mathematical tools that we have, are not sufficient for answering Hilbert's first question. So we don't know that how many real numbers are there. We just know that assuming consistency of ZFC, we can answer this question directly. So here comes the universe view, which I briefly explained before getting into the multiverse view. Well, what is the universe view? The idea is that there is a unique ideal mathematical universe in which every mathematical question has a definite answer, including that of Hilbert. So our idea is that every axiomatization of mathematics is a description, actually, just a description of the unique ideal mathematical universe. This is actually the so-called Platonic view in mathematics. So we conclude that while no description of the mathematical universe could be complete enough to answer all mathematical questions, but a good description is supposed to provide enough tools to answer the most fundamental mathematical questions, such as Hilbert's first problem. Thus, ZFC is not a good description of the ideal mathematical universe in this multiverse view. So it's not does not capture the full picture. So I chose the elephant in the dark room title for this slide particularly. You possibly heard the story of Rumi, in which in the book of that somebody brings an elephant from India, Iran, where people never saw such an animal, and put it in the dark room, in the city. Everybody joined to see what the elephant is. And everybody entered the room and touched the elephant. Somebody took its tail and said that maybe elephant is like a rope. Somebody touched his feet and told that elephant is like a column. So everybody had a description of the elephant in the dark room, and the truth became known when everybody brought some candles and lit up the room, and everybody saw the true shape of the elephant in the dark room. So here is the same approach in the multiverse view, where everybody is searching for candles to put light on the true shape of the unique mathematical universe, the Plato's ideal universe. So the universe view says that as a bad description of the universe, ZFC must be either entirely by some essentially different axiomatic system, which is essentially different description of the universe, or be modified by adding some currently missing fundamental axioms of mathematics, which is actually a completion of ZFC, with adding some additional axioms. Here begins the grand project of the foundation from a universe view, actually. Find a good description of the ideal mathematical universe. Assume philosophically that exists and it's unique. So there are quite a few of attempts in this direction. For example, the philosopher Quine proposed an entirely different set of axioms for mathematics called the Quine's continuations, which is a rather weird set of axioms implying that set of all sets exist, but certain type of sets could not be constructed, and essentially quite different from ZFC. In the other approach, which is the modification approach or completion approach, where you try to improve ZFC, there are quite a few of approaches that are being followed by contemporary mathematics theorists all around the world. So the first approach is the ZFC plus log axioms. This is actually the Gödel's project, that you add some large kernel axioms, some strong axioms of infinity, some versions of infinity, stronger beings in the universe, and in the hope that it resolves your incompleteness in some degree and settles your questions in math work, just the continuum hypothesis, for example. Another approach is to add axioms that imply that the universe has a very finely defined structure, such as the constructivity axiom B equals L, which tells you that the universe, every set in the universe is actually definable and very well behaved, in the extent that it actually limits the size of your universe to a very narrow body of sets. Another approach is forcing axioms, such as proper forcing axiom, which are a quite different type of axioms. Some of them has large kernel strength, and for example, some of the large kernel axioms may imply that continuum hypothesis is actually false, and the size of continuum is exactly Aleph2, and settle the questions in another way. So they are part of the project in ZFC. There is another version, so that you possibly know that the large kernel axioms are quite different in nature from the constructibility type of. So constructibility type of axioms actually say that the universe is very narrow, is very poor in size, it's very small. But large kernel axioms actually imply that the universe is very big, full of unconstructible objects, such as a measure on a measurable carton, things like that. But some people like would actually try to combine these two and add nice features of both approach into one single ultimate L principle, which actually is consistent with large kernel axioms, and the construction of Boudin's ultimate L is in this direction, which in some sense it's actually a demonstration of the true face of the Plato's ideal mathematical universe. So these are the approaches in universe view. Opposing to this view and these approaches, which are alive in the mathematics, there is another approach emerging in the past few decades by Joel Hamkins and quite many other organizations, which is called the multiverse view. So before jumping in multiverse view, let me add some background so that I can explain to you forcing, and then go from that to the actual description of the multiverse. Okay, so forcing. Before getting into the forcing, which is actually material that inspired all the multiverse view, we are all familiar with the idea of expanding universe in mathematics. Not in but in some local universes. You live in a universe, say in the field of real numbers, and you come across some problems, which is using the existing material in your universe, but its solution could not be found there. For instance, the problem of finding a root for the equation x2 plus 1 equals 0 in R. the equation itself is completely meaningless. So for somebody who knows only real numbers and algebraic equation can completely understand what x plus 2 plus 1 equals 0 is, but he cannot find a solution for it in R. So he can imagine an imaginary solution to his problem, say I, and then expand the universe to another one, which is not too different from your original universe. For this case, R is to C, which is itself a field, so not too unfamiliar, but has the additional nice property of containing I and solving x 2 plus 1 equals 0. So this is a common process in mathematics that happens time and time and again everywhere in the mathematics. So forcing works the same way in some sense. So in a mathematical universe, V is a model of ZFC, and you have a problem there. What your problem is to find a special kind of filter, which is called the generic filter, on a partial order P in the universe V. You cannot find it anywhere in V. So you have a partial order P in V, so you can understand P, you can understand the notion of a generic filter. All is familiar for you, but you cannot find the filter itself in your universe. You imagine this generic filter to be G as a solution to your problem, and then expand your universe V through the method of forcing to a universe called G, which is not too different from V in the sense that it contains the same ordinals and have some same properties, but it's a little bit different in the sense that it contains the filter G and it has potentially more nice properties and lots of additional statements such as hypothesis or the negation of continuum hypothesis or many more statements are true in it. So VG actually contains new mathematical objects and additional properties. So that's how forcing works, just like a field extension in your normal mathematical practice. So how the universe view sees forcing? Well, when forcing was invented, there is a lot of new results obtained by method of forcing, a swarm of independence results flowing everywhere, proving all manners of consistency results and all manners of new universes via different methods of forcing. And the method actually sectors with a very strong tool to construct huge deal of mathematics, a very diverse set. So the universe view actually sees this phenomenon as a sign of ultimate weakness of the ZFC as a description of mathematics, and so validates its view as the necessity for completion or modification of ZFC. So this is the universe first. But the multiverse view reads the sign another way. So they say that the vast number of equally interesting mathematical universes constructed by forcing indicate that there is no standard and unique ideal mathematical universe as opposed to the Plato's view. Instead, we are facing a network of distinct but connected mathematical universes, multiverse. So multiverse view brings up some issues in universe view. They say that there are certain expectations from universe view which are not satisfied, at least for now. These expectations actually tell us that we should move on beyond universe view. What are the expectations? First, the universe view must be able to produce a basic mathematics. In those, all fundamental mathematical questions could be settled, but such theory is not achieved yet. Or at least there is no consensus, there is no agreement on the what this base theory should be. They also say that the independence phenomena in such a base theory must be limited to where paradoxical-looking statements, such as Gödel's statements, which are constructed in a very way and not so natural, but not the simple questions of the daily mathematics, such as the continuum hypothesis, which is a very, very simple question: how many real numbers are there? So we should not run into independence results or in a situation in very simple and basic questions like that. The other expectation of from the universe view is that the few independence results that happen in the base theory could be resolved by using new intuitively viable natural axioms. But even for the continuum hypothesis, there is no general agreement on how to solve this, how to settle this axiom, this statement, and this question. So we don't know actually what is the natural expansion of the ZFC. Somebody says that it's constructivity. Somebody says that it's large cardinals. Somebody says that it's proper. It's a forcing axiom. So there is no general agreement on what to do, what to add to ZFC. We can settle it in different ways, but which is natural, and there is no indication. So another basic expectation is that the basic theory and structure of the set-theoretic universe should become increasingly stable and widely accepted among set theorists and mathematicians. So multiverse view says that, well, it seems that you are not going to action, and it seems that you are not progressing in this manner. And a good analogy that can bring your mind closer to what the multiverse view is trying to say here is a geometric one. For example, you know that it's often repeated in the multiverse view that there are different concepts of sets in different models of ZFC, or at different forcing extensions of a certain model of ZFC, which is like different concepts of point and line in various non-Euclidean geometries, which all are models of Euclid's first four except the fifth one. So in hyperbolic geometry, you have a certain type of a line. In spherical geometry, you have another different type of line. Both are lines, but they are different notions of line, different interpretation of the notion, concept of line in these. So the same for the notion of set. So the set varies from model of ZFC to another model of ZFC, just like the notion of line varies from one type of to another type of geometry. So the situation clarifies here. So the universe view is actually the old question of geometry, that which is the true geometry of the universe. So no, we know that beyond this question, we did not solve that, but we just simply passed the question that what is the true geometry of the universe. We simply accepted all the equally interesting and consistent geometry beside each other and formed a kind of multiverse of geometry. And each of them are interesting in their own right, have their own applications and intuitions and theorems. So multiverse view is advocating for this approach to mathematics and saying that, well, don't search for the true universe and just move beyond that question, and without solving the true answer of the everything, finding the truth of the statements such as the continuum hypothesis, just accept all the possibilities. Well, the relative consistency result in set theory could be stated in this form. You start from C axioms and do some processes and get a model of another theory such as ZFC plus psi and another axiom. And then you prove the relative consistency of the latter theory in respect to the former. So the arrow connection here could be anything, could be a forcing construction. For example, where you expand the universe by adding new elements, or you can move from one set of axiom to another to a model of one set of axiom to another set of axiom via large cardinal ultra product, where you obtain a universe by making an ultra product of a universe based on a nice ultra filter that exists on a large cardinal, such as a measurable cardinal. Or you can go for inner model construction, where you can shrink the universe to find a smaller mathematical world inside it. Well, the multiverse of mathematical universes could be studied through any of such relations which connects two mathematical worlds to each other. So there is a connection between these worlds as well. To put it in contrast, let's re-emphasize on the different approaches to the continuum hypothesis problem of Hilbert's first problem. The universe approach is that the goal is to discover whether the continuum hypothesis actually holds or fails in the unique ideal universe of mathematics, the true shape of the elephant in the dark room. In this sense, Hilbert's first problem is still low, so nobody provided an answer. How many real numbers are there? Are there out of 10, out of 1? Nobody saw the actual shape of the continuum in the unique mathematical universe. But the multiverse approach to CH is that the goal is to analyze how the continuum hypothesis behave in the connected network of mathematical universes. We will see that in this sense, Hilbert's problem is settled. As opposed to the unique view, where we look for the truth or falsity of mathematical statements in the universe, we use the switch button terminology, which referring to the state of mathematical statements in the mathematical. So you go from word to word and see that a particular statement, how the truth value of a particular statement varies in the fabric of the multiverse, the whole world. So in this sense, what I switch a button, for example, given any model of ZFC, such as V, there are forcing extensions VG and VH, such VG collapses no cardinal and is a model of the negation of continuum hypothesis. But VH adds no reals and is a model of continuum hypothesis. So from any given model, any given universe of mathematics, you have a pathway to one universe and another universe. In one, you lose the continuum hypothesis and it holds. So you have two pathways from every universe to a correct and a version of continuum hypothesis. So it says that the CH is a switch in the multiverse. Well, we come back to this definition later on in this lecture. Well, so we told that the multiverse view is going to describe a multitude of network of mathematical universes connected to each other with some relation. And somebody may ask that, well, what's the shape of this multiverse? This multiverse could not be shapeless. How these all parallel universes are connected? So you can make an analogy between physics and mathematics also here. So some sectors who chose the multiverse approach speculated on the possible general properties of our multiverse, such a huge connected models of ZFC. These are mainly based on works of Hawkins and where he wrote in what he wrote in his papers. Well, the unique thing is that, well, we are going to provide a description. So we naturally, as a logician, we are going to provide some axiomatization. So we are approaching an axiomatization of the multiverse itself. The universe maxim in the unique ideal mathematical everything is absolute and has a definite state. It's either true, either it's a certain fixed, determined situation. But the multiverse maxim, upon we are going to provide a axiomatization of the multiverse is as follows. In the network of mathematical multiverse, everything is relative and has a changing behavior. So we expect the multiverse to be a diverse in which the Copernican principle holds. So in some sense, no particular point or universe in this multiverse is special. So we will see how this expectation, this maxim reflects in the axiomatization of the multiverse by Hampkins. Well, the first expectation is expectation of ours from the multiverse is closure under definability, which is where if a the multiverse is if V is a universe in the multiverse, a point in this multiverse, and W is a universe definable in V, then W is also in the multiverse. So the multiverse is closed under definability. So consequently, for any given model of set theory in the multiverse, all of its inner models such as L hot, LR, as well as its large kernel based ultra powers are in the multiverse because they are all good. So this is natural. Another closure property that we expect for the multiverse to have is that if V is a universe in the multiverse and W is a set forcing it V, then W is also in the multiverse. So if you construct a new word by alter extension or forcing, the new word is also part of the multiverse, and this is very natural. This is actually the natural way that we thought about multiverse in the first. So the multiverse is closed under forcing as well. And here we come to relativity in the multiverse, the mirror of tallness. So every universe V in the multiverse, there is a universe W in the multiverse, which V can be elementarily embedded in an initial segment of W, namely for some V embeds to W theta for some ordinal theta. What is this saying? This is saying that multiverse looks like the Gulliver's world. So in which call this story, Gulliver first reached a city, Lilliput, in which he was the tallest guy in the city and huge in comparison with other inhabitants of that city, and then sailed for another city in which he was very short and everybody else was so tall and huge in comparison with him. So in the Gulliver's Adventures multitude of worlds, Gulliver's multiverse, so to speak, you find differences that are quite different in tallness. So nobody is actually the biggest one or the smallest one. Again, the Copernican principle is revisited. So while each model of ZFC imagines itself as a very tall universe because it views itself as its axis of as a plus, so it's larger than any large cardinal from a perspective. Then the multiverse says that in the multiverse it's such a big place, that you can always find another universe which considers this universe very short. So for any Gulliver in this multiverse, there is another person that sees it as a Lilliputian. The same for the largeness, the mirage largeness says that not only tallness of the models, but also the size of the model. For the size of the models, we have this relative situation. So for every universe in the multiverse, there is a universe W in the multiverse which V seems countable from W's perspective. So each model of ZFC imagines that it's very large because it's a proper class from its own perspective. But multiverse is just huge place where you always can find another universe which views this universe very small. This is situation similar to Stone's paradox as well. So we expect multiverse to be such a rich place and always go for a bigger uh, model. So also the universe, there is a mirage of well-foundedness. So for every universe V in the multiverse, there is a universe W in the multiverse, which W seems not well-founded, V seems not founded from W's perspective, which actually says that there's no really truly well-founded universe in the fabric of the multiverse. So if a model thinks that is well-founded, it's just lack of perspective, lack of knowledge about the extent of the deep extent of the chain of membership chains in its models. So imagine it this way: in our world, we can, if we divide a material to elementary and more elementary particles, we reach a, say, that is indivisible. So there is nothing that is smaller than that. It says that in the multiverse, even if you live in a universe that it seems to have an atom or some end and the chain membership, there is always, it's just because the chain is invisible to you, this infinite chain of membership of sets of your universe, the atoms of your universe, and the bottomlessness of that is just invisible to you. So if you move to a richer universe that can see that chain, it can see that from outer perspective that your universe is bottomless as well. So why does the same as a well-founded universe, the multiverse is full much better universes in some sense, that you always can find another universe which we use this universe as non-well-founded, because it can see the infinite chain that exists in your universe, but it's not visible to you who live in your universe. There are some outer relativity principles as well that we expect for us to have. In a universe, we have an internally definable embedding of the universe. If this is a phenomenon that usually occurs in the presence of large cardinals as large as measurables, for example. We may iterate the process in a chain of embeddings and inner models as follows. For example, so you live a universe and you have a large cardinal and you get an embedding based on that large cardinal, and you can iterate the process and construct a chain of models. So the next axiom states that in the multiverse, there is no original reference point or reference universe for the embeddings. So any embedding has already been iterated many times. So your universe is in nowhere, in no sense, special. So it's not the beginning of any chain of iteration. So for every universe in the multiverse, every embedding in V, there is another universe W in the multiverse and an embedding H from W to V such that J iterates H. So your universe is never the only beginning of iterated embeddings in the multiverse. So they are outer relativity principles. Another technical expectations and axiom that we would like for the multiverse is a special technical phenomenon that not only every set contains a constructible universe inside it, such as the Gödel's constructible universe, but it also can be contained in a constructible universe as well. So not only internally, but also externally could be part of a constructible universe. And the next axiom states that any universe in the multiverse could be absorbed in a constructible universe. So the definition says that every universally multiverse is a countable transitive model in another universe, the average universe, which satisfies the axiom of constructibility. So we provided expectations in the sense that we expect multiverse to have these properties based on that maxim that we had back in the back of our mind. And our question is whether our description of the multiverse is consistent. These axioms that we presented form a constant set of axioms. Well, here Gitman and Hampkins, presuming the consistency of ZFC, the collection of countable, computably saturated models of ZFC satisfies all the multiverse axioms. So these axioms are completely consistent. There is actually a model for that. There is a model of multiverse, say computably saturated. Well, now we approach another view towards the relation between multiverse view and disciplines of foundation of mathematics or logic. So one relation comes in the sense of modal logic that you possibly have felt through the talk and by the language that I use in the possible words, connection words. This is actually a language of modal logic. So in modal logic approach, you make each forcing extension built upon a given universe as a possible word related to it with the forcing relation. In this multiverse could be seen as a giant crypto model where the accessibility relation is forcing. So here we can interpret the possibility and necessity in forcing terms in the sense that a statement phi is possible if it's forcible. Namely, there is a forcing extension which phi holds. A statement phi is necessary if it holds in all forcing extensions. So forcing extension is a possible word that we have an access to from a ground model. So it's necessary if in any possible word you can move to, you find it true. And it's forcible or possible if at least some word that you have to, you can move to that word and find it true. Well, here's the exact definition of switch from button as Hampkins proposed. A statement phi switch if both phi and negation phi are necessarily possible, namely, for example, something like CH. So you always can force it, make it, and you always can make true or it's necessarily possible. Statement phi is a button if it's possibly necessary, namely you can move to a certain universe and then make it true, and that's true from this point onward. So it's a button. Unlike a switch that you can change the truth and falsity of the statement anytime that you want. A button, when you put, then there is no turning back. So a statement like omega 1L is countable is such an example. So when you make it true, remains true. But CH, you can always make it true and make it false and again make it true and move. Well, every statement in set theory is either a switch or a button or the negation of a button. These are just. Well, the question is what model principles certain hold for forcing? So ZFC probably, I mean, certainly. For example, we know that this principle, say box phi implies phi, holds for forcing because the model of ZFC is the trivial forcing extension of itself. So every statement that is true in all forcing extensions is true in the ground model as well, trivial. A statement like this also holds for forcing. because if a statement is not true in any extension, then its negation is true in all forcing extensions. So this one is also holding in this. No. What is the exact set of model axioms that hold for ZFC and for forcing? Sorry, for forcing. Again, Hankinson law proved that if ZFC is consistent, then the only ZFC provable valid principles of are exactly those of S2, namely these principles, K dual S for 2. This is these forcing holds these axioms, but and only these axioms necessary. But you can also ask whether certain type of model axioms are also consistent with the behavior of forcing. For example, what about the maximality principle? Is it possible relatively consistent with I mean by possible? Is it consistent with ZFC for forcing to have such a property? Is not essentially part of its essential properties. Yes, you can provide some consistency results as well. For example, Hamilton's and Stabi-Mananen prove that the maximality principle is relatively consistent with ZFC. So one can build a mathematical universe in which any set theoretic statement phi that holds in some forcing extension and all further extension already true in all forcing extensions. So the maximality principle holds. So the obvious result is that if ZFC is consistent, it's consistent with ZFC that all S5 assertions are valid principles of forcing. Consistent. Well, another discipline that we are going to explore its connection with multiverse view is the potential. Actually, basically deals with the modal logic view of verse, with the slight difference that here we are dealing with all manners of possible words constructed from a given word, rather than forcing extensions. Forcing extensions are just a type of universes that you can construct from a given universe in set theory. There are lots of ways to move beyond. So different interpretations of the possibility model in set theory gives you different views, potentially different of the multiverse. So you can form the multiverse based on different types of relations between models. So phi is possible if it holds, for example, in forcing the way that we explained so far. You can interpret possibility in the rank way, so in the rank sense. So you say a statement be possible if it holds in a larger rank of one human word. So this could go. So this could be also another interpretation. You say that it's possible in the Goethetic sense, which means it holds in a Goethetic universe, which is a B kappa universe for kappa inaccessible. Or you can consider to be possible when in the CTM sense, in the countable transitive model sense. So there is a larger countable transitive model of ZFC in which phi holds. So you say that it's possible. Or an outer model, a generalization of the forcing, a random outer model of V. Well, another way to the situation is that, well, forcing is in some sense upward construction. You can look at an inverse forcing. You can look at your universe and say whether it's forcing the extension of something else or not. Well, the theoretic geology takes a dual approach towards forcing multiverse by trying to find whether a given model of ZFC is a forcing extension of the model of ZFC. Ground axiom says that this assertion the universe we has no non-trivial ground. So for fact, we know that many canonical models, such as L, L0 sharp, L mu, many instances of core models don't rise as a forcing extension of another model of ZFC, and so are models of the ground axiom. So you cannot go uh, to the bottom of these things. So you can define a some natural definitions. For example, W is a bedrock of V if it's ground of V and minimal with respect to the forcing extension. So you cannot go any further. You run into a bedrock in the grounds of the model. So W is a bedrock of V if it's a ground of V and satisfies ground axiom naturally. You cannot go any further. You cannot dig deeper. So Ritz proved that it's relatively consistent with ZFC that the universe has no bedrock model. So such models are bottomless. You can always dig. There are some certain units of mathematics that you always can go deeper and deeper. And the mantle is the intersection of all grounds of a model of ZFC. But whether it's itself a model of ZFC, well, Uzuba proves that are set directed, and so is a model of ZFC. And furthermore, assuming the consistency of extended very strong large cardinal axioms, mantle itself a ground of the universe, actually the smallest one, because the intersection of all ground. So you may think about a kind of paradigm. So you are given a model of ZFC, a universe, and you think for yourself, what are the essential parts of creature that I have? What part of these sets that are included in the universe are actually could be added by a forcing process? So there might be some core to each universe that if you remove everything else that is added by forcing to that universe, you reach to it. So this is a question. Ancient paradise idea, there might be a very natural inner model of ZFC lying beneath the surface of any universe. An ancient paradise which could be found after one removal but possibly have been added to it through deemed man-made, so-called forcing constructions. So Fuchs, Hampkins, and Ritz prove that every model of ZFC is the mantle of another model of ZFC. So all mathematical universes are the same in this regard. So nothing special here. Here come to the conclusion of my, so you may consider all or none of the mathematical universes ancient paradise because of this result, depending on whether you believe in heavenly nature of and what contributes to us. So there is nothing interesting to explore, at least in this approach. Okay, thank you for your attention, and if there is any question,
all right. Thank you, Ali. There are a few questions. A very good talk. The first one, can there be non-standard natural numbers in multiverse?
Could I qualify that? Hello?
Oh, sure. Yeah. Yes.
Yeah, you focused on kind of higher set theoretic questions, but what about the status of unprovable number theoretic statements? Do they can you set sort of, do you have a view about, does the multiverse decide questions like that? For example, a pi01 statement, if it's consistent, then it's true.
Yes.
So if a pi01 statement is true in some member of the multiverse, it must be true in all of them. Is that a valid statement?
Well, I don't know. Well, I need to think about that. So maybe we can make it exchange in email. So let me think.
Well, for example, ConZF. I mean, is ConZF true in every member of the multiverse?
I think so. No. Well,
I mean, you're not really focusing on that. You're more interested in the continuum hypothesis, obviously, but where we really don't know the truth value, whereas ConZF, I think we do, sort of. But I was just wondering about the number theoretic, other unprovable statements at a much lower level.
So that's a really interesting question. So it needs its own approach to the multiverse. So you are focusing on the lower parts of it.
Yeah.
The very bigger versions. Yeah. So there are some results I get some results of dualism.
Yeah, because I think all the construction.
You know that result that Hamilton proved that if you move from universe to another universe, the notion of truth in a natural model of number theory at the end varies from one model to another model. So these might be related to each other. So it's not as straightforward that is for me to answer this question right away. So
okay, yeah.
Thank you.
I wondered if it was worth thinking about, because I used to be interested in models of piano arithmetic and yeah.
So I'm sure that Ali Inayat and have results about that. It's some recent exploration in this they are looking at how the nature of the natural model of piano arithmetic is changing from one model of ZFC to another model, and it's not stable. So there might be complexities in this. So it needs some accurate analysis.
Yeah. Okay. Thanks for that. Yeah.
Thank you, Alex. Thanks, Ali. We've got the next question. By T. Wouldn't the multiverse view render the foundation of mathematics on an uncertain or relative ground? How could the multiverse view be established non-relatively and absolutely?
Well, I'm not sure what you mean, but uncertain ground. It's in terms of Joel Hamilton himself, it's actually expanding the Platonistic view to a pluralistic view. So actually, in their view, all the universes in the multiverse actually exist. So in the fabric of multiverse actually, so you are just expanding your view, not making the relativity that I mentioned in my exposition is not actually about the notion of the mathematics itself, because they say that the same view as the multiverse view in. So you don't say that all universe does not exist, or if there is a multiverse, none of those also exist. You just say that these rules of physics that apply in all universe, the constants of physics that apply in your all universe, are not essential. So they may vary from one universe to another universe, but what actually exists, that's the multiverse. But the multiverse are actually the true axioms of the universe, the particular rules that exist in each and every multiverse here. So each and every universe. This is actually an external view. So there is two different types of views here. One applies to the entire fabric of the multiverse, which we actually axiomatize that and think as an solid set of experience. And then in a lower level, in each individual universe, you have ZFC and you have something, a valid ZFC plus on without continuum hypothesis. So I guess that well, we have discussions in two different levels. You also can apply this relativity view, the multiverse itself, for a higher multiverse in some sense that you possibly mean, but I would like to avoid this type of argument, because may actually push us to all turtles down situation, so that you move from a relativity concept to another relativity concept and beyond, and never reach anything to discuss about. So I hold the view that multiverse view is actually just an invitation, an encouragement for the mathematicians to move beyond traditional view of modification of ZFC and trying to resolve the statements such as continuum hypothesis in a vein. In their view, that it's a waste of time just to try to resolve the continuum hypothesis. Just that, because they are trying to prove a question that how many real numbers are there is actually a meaningless one in this sense. So you look at it in a different way. So that's I can say. Hope I could answer your questions correctly, but sorry if it's not what you meant.
Right. T, are you all right with the answer, T? Discussion. I think we just open up to discussions, you know. Okay. Any more questions? Are you free to ask questions? You can unmute and then just mention your name and just state your question. Oh, okay. He just replied. He says, yes, thank you. He couldn't speak because his mic isn't working. Yeah, thank you, T.
Oh, I just recalled part of Alex's question. So he asked, I guess you asked that if ZFC is correct in the whole multiverse. It's of course not, because it could be falsified, right? So
yeah, but conZF, yeah, but only in the non-standard model.
Stronger than ZFC. Naturally, it's stronger than ZFC itself, right? So
yeah,
but could be. There is a universe that it's correct there. You might.
Yeah, but that universe must have non-standard natural numbers.
Yes.
And all your constructions, as far as I could see, that the multiverse was closed under, preserve omega. I mean, they don't give any new natural numbers, do they? Although then something you said that you could just take all the recursively saturated models, and they of course have non-standard natural numbers in them. But that was my first question about whether you ever get a non-standard omega in the multiverse. But
I guess they but I should look at the Joel and Ali's analysis of non-standard models in models of ZFC, non-standard models of piano arithmetic in ZFC. I cannot answer that right away because I need look at the proofs there. So how can they relate the? So that's a really interesting observation. Thank you, Alex. Yeah.
Okay. Yeah. Well, thanks for the talk.
All right. So, thank you so much for the discussion again. Any more questions or any more thoughts, Ali, that you think of and you go like, oh yes, something else you add?
Well, I would like to clarify my own position that I'm not a defender of multi or either the the universe view. I used to be a Platonist, and I still have passion for Platonism, but well, I am agnostic in this case, and there is actually competition between two schools. One prominent is actually Hugh Woodin for the universe view. They are actually powerfully trying to bring the project into a company. At the same point, Hampkins and his team, and also Cy Friedman, are trying to promote some multiverse views, and I'm just watching the match to see which paradigm uh, will uh, will prevail in the end. So it's an interesting time to be working in the foundation of mathematics, because we are in seems to be in the cusp of a revolution in some sense. Yeah.
All right, thank you. I think we're running out of time. So the next session will start in a couple of hours time. Thank you, Ali, for your talk, as well as Sue. I'm not so sure if he's still here. So thank you so much to the two speakers today, and thank you to those who have attended the first half. Very good talk, all of them. So we'll catch up again in a couple of hours. I'm not so sure where you are, but in Malaysia, we are 7 o'clock now. So we will continue at 9 o'clock, resume at 9. So where you are, two hours later, we'll be here half an hour before. I think Zhu is not gonna, he's gonna leave the Zoom on. So yeah. All right, so we'll see you in another couple of hours. Okay, for another 2 brilliant speakers. Thank you so much to both speakers and all attendees today.
Goodbye.
Okay, bye now.
Bye.